In this talk, we're going to continue talking about generating functions. But now we're going to ask the question, can we create one generating function that will work for the entire sequence P of n? Remember, P of n is just the number of numerical partitions of the number n. We can use any number of parts, but they all have to be positive integers. So that means we can use any number of ones, any number of twos, any number of threes, etc. If n is a large number, of course, there'll be an enormous number of partitions for the number n. Can we create one generating function that will work for any n? Well, let's follow the strategy we've been using before. I'm going to look at g of x here, our generating function. I'm going to say, how many ones do I have? Well, we'll have a factor for the ones, and we could take 0 ones, that's just the 1, or 1 1, that would be our x, or 2 ones, that would be x squared, or 3 ones, or 4 ones, or any number of ones. So that would go on forever. This would be a power series, and a power series that you all should recognize really well. What about for the twos? I could take 0 twos, or I take 1 2, and that would give me an x squared here. Remember the 2, every 2 I use adds 2, so we want the 2 in the exponent there, so that when I choose this factor x squared, it will add 2 in the exponent of x. I could take 2 twos, that would be an x to the 4th, or 3 twos, and keep going. I could use any number of 2s. I could ask, how many 3s do I use? Well, I could use 0 3s, 1 3, 2 3s, or any number of 3s. And I'd have a term like this for any number I want to use. In other words, I would have an infinite product of infinite series, infinite power series here. And that looks like a big, awful mess. There are some things we can do to write this a little bit more nicely. We recognize that this power series, 1 plus x squared plus x cubed, etc., can be written, you should remember this from your Calc 3 classes, as 1 over 1 minus x. This next power series looks the same, only we have x squared in place of x, so it's just 1 over 1 minus x squared. The next power series is just 1 over 1 minus x cubed, etc. So it's gotten a little bit nicer. Now I have my generating function. It's not even written as a power series, but we understand that 1 over 1 minus x has this power series representation. 1 over 1 minus x squared comes from this factor, etc. We can write our generating function as this product of functions of this form, and it's an infinite product. How do we get P of n? Well, P of n then, the number of partitions of the number n, is the coefficient of x to the n in the power series expansion of this function. G of x. So can we use that to find P of 5 or P of 10? Well, here I've written down again what G of x is. It's this infinite product of infinite series, of power series, which we can write like this, or in compact notation, we can write it as the product from k equals 1 to infinity of 1 over 1 minus x to the k. That will give us each of these factors in the product. Now, that doesn't help us expand it. We can use a computer to compute the beginning of the expansion, and we get the generating function for the partition numbers is just 1 plus x plus 2x squared plus 3x cubed plus 5x to the 4th plus 7x to the 5th plus 11x to the 6th plus 15x to the 7th, etc. Now look at the sequence of the partition numbers we get. 1, 1, 2, 3, 5, 7, 11, 15, etc. It starts out in a way that kind of looks familiar. 1, 1, 2, 3, 5. Do you recognize that beginning of a sequence? I'll let you think about that. But then you'll see it has these numbers that you probably haven't seen before. I mean, you've seen each individual number before, but you probably haven't seen before in this sequence. It's a rather mysterious thing, this partition number sequence. What is P of 5? How many partitions are there of the integer 5? Well, we just go here and we look at the coefficient of x to the 5th, and that's 7. So P of 5 is 7. We can check that. How can we write the number 5? Well, we can just write it in one way as 5, or we can write it as 1 plus 1 plus 1 plus 1 plus 1. We can write it as 1 plus 1 plus 1 plus 2. We can write it as 1 plus 1 plus 3. We can write it as 1 plus 2 plus 2. Or we could write it as 2 plus 3. Or we could write it as 1 plus 4. We have 7 ways here. I claim that's all the ways to partition the number 5 as a sum of positive integers. That's just the page number. See if you can check that these are in fact all of them. What is P of 10? How many ways can we partition the integer 10? Well, we go up here and we see P of 10 is 42. That's starting to get to be a pretty big number. I'll leave that to you guys as an exercise. Try to write down all 42 ways to write the number 10 as a sum of positive integers. I'm sure you can do it if you give it probably 5 minutes. It won't take that long. It'll be a fun thing. Make sure you get all 42 of them, though. Can we look at other generating functions in a similar manner? Here's an interesting one. We're going to look at this combinatorial function. P, that's the letter O. P sub O of n is the number of partition of n into odd parts. For example, we've seen that there are 7 ways to partition 5 into parts. 7 ways to just have a numerical partition of the number 5. What is P sub O of 5? How many of those use only odd parts? And we can go back here to the previous page and we can see this one uses only odd numbers. This one uses only odd numbers. This one uses a 2. This one uses only odd numbers. This one uses 2s. This uses a 2. This uses a 4. So how many ways are there to partition 5 using only odd numbers as parts? The answer was 3. There were only 3 of them. How can we get a generating function O of x for P sub O of n? When I say a generating function, remember this is what I mean. I haven't written things this way before, but this is a common way to understand a generating function. If we write our generating function as a power series, the coefficient on the x to the n term is precisely this sequence here, P sub O of n, so that you can compute P sub O of n just by looking at that x to the n term in the power series expansion, and the coefficient will be that number. So how are we going to create the generating function? Well, we can use any number of 1s. So we're going to have a factor that looks like this, just like the beginning of our previous generating function. We can't use any 2s. So our next factor will correspond to 3s. That should be a 6 here. This will correspond to no 3s, 1 3, 2 3s. Let me make that a little bit clearer here. We can't use any 4s, but then we'll go on to 5s. We can have a 1 plus x to the 5th plus x to the 10th, and we keep going as many 5s as we want, and we keep going. Just like before, it's an infinite product of power series. And if we want, we can write that as 1 over 1 minus x. That's just what this power series represents. You learned in calculus that this 1 over 1 minus x function is exactly equal to this power series involving x, at least when the absolute value of x is less than 1. So as a formal power series, we'll just write that this is the same as 1 over 1 minus x. The next factor is just 1 over 1 minus x cubed. The next factor is 1 over 1 minus x to the 5th. And we keep going like this. So we have a brand new generating function for a brand new combinatorial problem. This will tell us, when we expand this and look at this as a power series, the coefficient on x to the n will tell us how many ways we can write n as a sum of odd numbers. Let's look at another one, and I think there was an exercise like this, at least for a special, in a certain special finite case. Can we find a generating function? I'm going to call this q of x, which is a common name for it, for what the book calls p star of n, the number of numerical partitions of n into distinct parts. When I say into distinct parts, I mean you can't use any number twice or more. So for example, what is p star of 5? Well, you could write 5 just as 5. That's just one part, one distinct part, it's fine. You can write it as 2 plus 3, or you could write it as 1 plus 4. We're not allowed to use ones twice, so we can't write it as 1 plus 1 plus 1 plus 1 plus 1. That uses the 1 over and over again. We can't write it as 1 plus 2 plus 2. There are just these 3 ways to do it, so p star of 5 equals 3. Just to preview what's coming, notice that p star of 5 is 3, and p sub o of 5 is 3. Is that a coincidence? Well, here you might think very well, this is just one tiny example. Of course, that just might be, a random thing. We'll see. So how do we get a generating function for p star of n? Well, we can use ones, but we can only use at most one of them. We're allowed to use 0 ones or 1 1. So we have a factor in the generating function that represents our choice of 0 ones or a single one. We can use 2s, but we can only use none of them or one of them. We can use 3s, but we can either use no 3s or 1 3. And it will keep going on like that. So q of x, this generating function for p star of n, is just this infinite product of these very simple factors. And if I expand that out into a single power series, the coefficient on x to the n will be exactly p star of n. Now here's an amazing thing. We just showed above that O of x is this infinite product of functions of this form. And we also just saw above that q of x is an infinite product of this form. Euler, this is in the 18th century, the great mathematician Leonhard Euler, showed that these two infinite products are actually identical. They're always the same thing. And before we even demonstrate that that's true, what would be the consequences of that? That would mean that O of x, which is the generating function for p sub O of n, the number of partitions of n into odd parts, is the exact same function as q of x, the generating function for p star of n, the number of partitions of n into distinct parts. But if the generating functions are identical, then when you expand each as a power series, they'll have the exact same coefficient on x to the n for every n, and that will tell us that p sub O of n is the same as p star of n for all n. We saw that for n equals 5, just happens to be true that they're the same. But the claim is, since these generating functions are identical, these combinatorial quantities are in fact identical as well. Before we look at an example, let me show you Euler's beautiful argument that these two are really the same function. Look at O of x. It's this infinite product here. I'm going to write this infinite product in what will look like a strange way. I'm going to multiply top and bottom by 1 minus x squared. So on the bottom here, I have 1 minus x. Now, because to cancel out what's on top, I'll have 1 minus x squared. And then I have this 1 over 1 minus x cubed. So what I'm going to do is I'm going to multiply the top. Let's see, on the bottom here, sorry, I have 1 minus x cubed. I'm going to multiply on the top and bottom by 1 minus x to the fourth. So I'll put the 1 minus x to the fourth on the bottom. Notice that before on the bottom here in the denominator, I only had factors 1 minus x cubed, 1 minus x to the fifth, only using odd powers of x. But now I'm putting similar factors on the top and the bottom with even powers of x. So the next term I already had on the bottom was 1 minus x to the fifth. But now multiply on the top 1 minus x to the sixth over 1 minus x to the sixth. I already had on the bottom 1 minus x to the seventh, so I'll multiply on the top here by 1 minus x to the eighth, and then put the corresponding 1 minus x to the eighth on the bottom. And then we keep going like this. These two are identical because the only thing I did was multiply by 1 minus x squared over 1 minus x squared, 1 minus x to the fourth over 1 minus x to the fourth, 1 minus x to the sixth over 1 minus x to the sixth, etc. And that doesn't change anything. But now what happens? Look at 1 minus x squared divided by 1 minus x. Remember here, 1 minus x squared, just factor it, it's 1 plus x times 1 minus x. And dividing by 1 minus x cancels the 1 minus x there. I'm left with 1 plus x. That's when I look at this quotient. I get the 1 plus x. Look at this quotient, 1 minus x to the fourth over 1 minus x squared. Well, that's exactly 1 plus x squared. That's this piece here. Look at this next quotient, 1 minus x to the sixth over 1 minus x cubed. That's just 1 plus x cubed. That's this piece here. And then keep going. 1 minus x to the eighth over 1 minus x to the fourth is just 1 plus x to the fourth. And so on and so forth. And that's exactly what we already had for q of x. Here we're not worrying about any convergence issues, just as formal functions here, we get the exact same thing. Conclusion is a combinatorial conclusion, that p sub o of n is the same as p star of n for every n, because their generating functions are identical. We've already seen the one example that p sub o of 5 is the same as p star of 5. Let's look at another example. Let's compute p sub o of 6. How many ways can we write 6 as a sum of odd numbers only? Well, of course we can write 1 plus 1 plus 1 plus 1 plus 1 plus 1. We can write 1 plus 1 plus 1 plus 3. We can write it as 3 plus 3. But we can also write it as 1 plus 5. And you'll see these are the only ways to write 6 using nothing but odd numbers. So how many is that? That's 4 ways to do it. What is p star of 6? The number of ways to write 6 as a sum of distinct parts. Well, 6 can be written as 1 plus 5. It can be written as 2 plus 4. It can be written as 1 plus 2 plus 3. It can also be written just as 6. Again, 4 ways to do it. So these are just some examples that show that p sub o of n is really the same as p star of n. Here's a question I'll leave you with, which is when you see that these two combinatorial problems have the same answers, it's natural to ask, is there a purely combinatorial proof of this fact? What we demonstrated is they have the same generating function and thus are the same sequences. But a combinatorial proof would argue something like this, that there's a nice one-to-one correspondence between each method. For example, when n is 6, each method of writing 6 as a sum of odd parts with each method of writing 6 as a sum of distinct parts. And let me tell you, one can construct a proof like that. Try to show some sort of natural correspondence that would let you be completely convinced that no matter how big n is, you can take every partition of n into odd parts and map it one-to-one onto a partition of n into distinct parts. It's a little bit tricky, but it's fun to try to find this, and we can discuss this in class sometime soon.